and for unit ramp input, right? For unit step input, we have observed that for type 0 system, the error is a finite value. If the type is 1 or more than 1, the steady state error becomes 0. And one more observation is steady state error can be calculated as 1 divided by 1 plus Kp, where Kp is the static position error constant, which is limit s tends to 0, GFS multiplied by HFS, right? Then for ramp input, we have observed that for type 0 system, steady state error is going to infinity. And for type 1 system, we are getting a finite error. It depends upon the value of system gain. And if the type is greater than or equal to 2, steady state error is 0. And it can be calculated as 1 divided by Kv, where Kv is the static velocity error constant. Okay. Now, one more we have to do. Actually, this we have missed in our first unit. Right? Means different types of test signals. We have seen that it is step signal, ramp signal, then sinusoidal signal, impulse signal. Actually, one more signal is there. So this also you have to do it. That is steady state error. Sorry. Steady state error to a parabolic reference input. Okay, so what is parabolic input? Is t square by 2. So this is the nature of the waveform, t square by 2. So if you plot the waveform of parabolic input with respect to t, it will be a parabola like this. So as like ramp input, you can observe that this parabolic reference input also an unbounded input, right? When t tends to infinity, it will go to the infinite value. Okay, so we will continue the same analysis. So in order to find the steady state error, we need R of S. So what is the Laplace transform of t square by 2?
1 by s square, sir.
1 by s square or s cube?
1 by s cube, sir.
Yeah, fine. Okay, now we can calculate the steady state error. What is the equation for steady state error? Is limit s tends to 0, s multiplied by R of s divided by 1 plus g of s h of s, where g of s h of s is the open loop transfer function, right? So if you substitute R of s in this relation, we will get limit s tends to 0, 1 divided by s square plus s square g of s h of s. It can be written as limit s tends to 0, 1 divided by s square g of s h of s. So this can be again so like in other reference input, here also we are introducing one term called Ka, is static acceleration error constant. Okay, so limit 1 divided by Ka, where Ka is equal to limit s tends to 0, s square g of s h of s. Actually, it is easy to remember, right? For positional static error constant, it is just limit s tends to 0, g of s h of s. When it becomes velocity error constant, you have to multiply 1s, that is s into g of s h of s. Now for acceleration constant, again you multiply 1s, so you will get limit s tends to 0, s square g of s h of s, where k is called static acceleration error constant. Yeah. So like we conclude EFS is equal to 1 by Ka. This relation you keep in mind, and this also. Now we'll do the same exercise. We'll take n equal to 0, 1, 2, and see how this error is varying with respect to all those things. N, next one is Ka, next one is steady state error. Now, when n equal to 0, type 0 system, what is the Ka value? You substitute in the transfer function and tell me.
S square into K, sir.
S square into 0. Yeah, correct. K equal to 0. So obviously steady state error becomes 1 by 0, that is infinite, right? Now for type 1 system, yeah, for type 1 system, denominator 1 s term will come, right? Because s power n equal to s power s raised to 1, that is 1 by s. And s square and s will cancel. Numerator 1s remains. So if you put s equal to 0, the whole term will become 0. So again, K becomes 0 and steady state error infinity. And what about the type 2 system? So in type 2 system, n equal to 2, so 1 by s square will come. So in numerator also s square will come. So s square and s square will cancel. All other s terms become 0. So finally you will get system gain K. So you can get 1 by K. And if the type is 3 or more, what will happen? In denominator 1 s will come, right? So if s tends to 0, your K tends to infinity. So if K is infinity, steady state error will come. So if the type is equal to 3 or more, your steady state error becomes 0. So for a parabolic reference input, you can see that only for type 2 system, we are getting a finite error. Right? And also the value depends upon the gain of the system. And for type 0 and type 1 system, it is always infinity only. Right? So if it is going, type is more than 3, it is 0. Clear? So now what we will see some numeric examples. Please note down this question. A unity feedback system has the following forward transfer function. Forward transfer function, which is given as g of s is equal to k s plus 12 what you can do is s plus 5 take. S plus 5 the whole divided by s plus 6 and s plus 7 s plus 8. Okay, you have to find the value of k, find the value of k, in this case the system gain, right? So that there is 10% error in the steady state. So 10% error in the steady state. Okay, how will you find it? The forward transfer function g of s is given as k multiplied by s plus 5 divided by s plus 6, s plus 7 and s plus 8. So the question is find the value of system gain so that the system steady state error is 10%. How will you find? One thing it is observed that in question it is not mentioned that which input is going to give, whether it is step or parabola or ramp. Nothing has mentioned in it. So how will you find it? Tell me. Why? No. Yeah, we cannot tell any input from this. We will see. Okay. What is the type of the system? What is the type?
One, sir.
Type 4. Type 1. Yeah. I think you are confused. One second. We'll go back to the answer. So if you are writing in this form, type this n decides means the power of s. This n decides the type of the system, right? So in this, what is n? N is 1, right? Now one thing is clear, it is a type 1 system. And another thing we can observe is given the steady state error is a finite value, right? 10% means 0.01. So we are getting a finite value of error. Okay, now you go back to our analysis and check for which reference input type 1 system gives a finite steady state error.
Unit ramp function, sir.
Yeah, correct. Because for all other function, it is different, right? If we consider unit step response, we can see that for a type system, the steady state error is 0. So that means the input is not a step input. If you go to RAM for a type system, it is 1 by k, that is, it gives a finite value. So what about a parabolic input? For a type system, it is infinite. So we can conclude that the input is a step response. Sorry, ramp input, right? So first we will write that since system type is 1, the error stated in the given problem must apply to a RAM. Clear? So now everything is clear. Our input is unit ramp reference input. Okay, must apply to a reference input. Okay. So how will you find the steady state error for a ramp? 1 by kV, and this is given as 0.01. So no, not 0.01, right? Sorry, it is 0.1, 10%, right? Yeah. So what is kV? Kv is equal to 1 by 0.1, 10. So now our aim is to find the k. At what value of k the steady state error becomes 10%, right? So what is the equation for kV? Kv is equal to limit s tends to 0, s g of s, h of s, right? And in the given problem, what is the value of h of s? 1, right? Because it is given as a unity feedback system. So for a unity feedback system, h of s is equal to 1, and g of s is given, right? So we can write kV is given as 10. So 10 is equal to limit s tends to 0, s multiplied by g of s is k s plus 5 divided by I think, yeah, this s plus 6, s plus 7 multiplied by s plus 8. So this s and s got cancelled. So finally we'll get 5k divided by 6 into 7 into 8. So what is the value of k? 672, correct. So at k equal to 672, so if the system gain is 672 in this system, if you apply a unit ramp reference input, the steady state error becomes 10%. Point. That is the meaning. Clear? Yeah, fine. So we will do one more example and we'll move to the next topic. Okay. Not on this question. Here also given it is an unity feedback system. So since it is a unity feedback system, you can take h of s equal to 1, and the forward transfer function, forward path transfer function, g of s is equal to 1000 s plus 8, s plus 7, s plus 9. Okay. So what you have to do is, first of all, you have to find the steady state error for the step ramp and parabolic input. You have to evaluate the steady state error for all the standard inputs, step, ramp and parabolic input. Okay, so do it fast and tell me the answers, because it is very simple, direct substitution. Okay. First you take step preference. Few things you can directly judge by seeing the type of the system. So the given system is type 1 system, right? Or type 0.
Type 0, sir.
Yeah, it's a type 0 system. So for some type directly you can write, right? If it is infinity means directly you can write it is an infinity. If it is final 0 also directly you can write. If it is a finite value you have to calculate it, right? Okay. So tell me what is KP and ESS for step input. So if it is unit step input, anyway, for type 0 system, you are telling KP or ESS? ESS. So what is the value of KP? 26.98. And what is the error value? 007. It's a finite value. Okay. Now, what about the others? Directly you can write, right? You don't need to evaluate it. For ramp input, what is KB? If it is type system, KV is 0, right? Yeah. So obviously steady state error becomes infinite. And what about the third one? For type 0 system, yeah, K remains 0, the steady state error becomes infinite. Okay, clear. So the type judges the value of steady state error. Clear? So if you have doubt, please ask. Clear. Okay. So now we have 20 more minutes, right? Yeah. We will move to the last topic in this unit. It is stability criteria. This is also very important topic. Right. Why? What is the importance of this topic? Okay. And we know standard form of our transfer function, right? What is the standard transfer function? Is equal to y of s. Oh, in polynomial terms, we will write is n of s divided by d of s, right? N of s is the numerator polynomial, d of s is the denominator polynomial. Right? What is the standard form? It is b s power m plus d1 s power m minus 1 plus up to b minus 1 s plus dm. What the denominator polynomial? It becomes a naught s power n plus a1 s power n minus 1 plus etc. up to a n minus 1 plus a. And we have seen that the roots of the numerator polynomial will be the zeros of the transfer function, and the roots of the denominator polynomial is the poles of the transfer function, right? And one more thing, we have seen that the characteristics of the system is decided by the location of these poles, right? So usually we will call this denominator polynomial d of s is called six polynomial, which decides the characteristics of the system. This was one, etc. plus a minus 1 yes plus a. This is called characteristic polynomial. Now, have you heard about Hurtiz polynomial in mathematics? Hurtiz? No. Okay. So we'll define first. It is what it is a polynomial is said to be Hurtiz if all its roots have negative real parts. Negative real parts. Hope now you understand what is the importance of this polynomial. Any polynomial is said to be Hurtiz when if all its roots have negative real parts, and according to Weber stability. What is the criteria for Weber stability? You have already seen, right? What is the criteria for Weber stability? Yeah, you tell me according to the location of the poles in the S-plane. That is the general definition, and we have seen that according to the position of the poles, we can decide the stability of the system, right? So according to the location of the system, how can we define the criteria for Weber stability?
Yes, sir. The poles must be lie on the negative axis.
Yeah, correct. Absolutely right. That means all the roots of the characteristics equation. Okay, I am writing a short C equals to characteristic equation or characteristics polynomial. All the roots of this characteristic equation should lies in the LHD of this plane, right? Right. And one more thing is in this polynomial, according to Hurtiz, so a polynomial is said to be Hurtiz if all its roots have negative real parts. That means all the constants in this polynomial, a naught, constants, the coefficients, a naught, a1, etc. up to an, are real numbers. Okay, here. And now one question would arise. Anyway, by seeing the location of the pole, we can see the stability of the system, right? Then why we need this kind of Hurwitz polynomial and one more condition? What is this? Routh Hurwitz stability criteria. That's obviously one question will arise, right? Now we will see why we need to go for Routh Hurwitz polynomial. Okay. So when n equal to 1, what is the denominator polynomial? It becomes a0 plus 1, right? For n equal to 1. So first order polynomial, it is a0 s plus a1, where a0, and what is the pole at this condition? For this one, what is the pole?
Minus a1 by a0.
A0. So in order to become the system in stable state, what is the value of a1 and a0? You are expecting? And this one thing is a1 should not be 0, a1 also should not be 0, right? If it is 0 means the pole will locate at origin, right? Yeah, if it is in the origin, whether it is whether we can call it a stable system or critically stable system. Critically stable system. So in order to become the system in stable state, both a0 and a1 should not be equal to 0. And another condition is, yeah, both a0 and a1 have the same sign. Same sign, right? Now, so using the polarity of these coefficients a0 and a1, we can simply judge whether the system is stable. For n equal to 1, for a first order system, we can simply judge it, right? Now we'll go to another second order system, n equal to 2. Again, the denominator polynomial can be written as a0 s square plus a1 s plus a2, which is a second order system. And from this, if we can understand that if a0, a1 and a2 are non-zero and of the same sign, d of plus is a Hurwitz polynomial. Right? So if the coefficients a0, a1, a2 all are non-zero values and all are having the same sign, we can tell it as a Hurwitz polynomial. We don't need to find the roots, right? While seeing the coefficients itself, we can see. If a1 is 0, what will happen? Yeah, repeated roots at where? So
On imaginary axis.
On the imaginary axis, right? So that is so our aim is to find whether all the poles are staying in the left LHP of the plane or not, right? So if we see the second order polynomial by seeing the coefficients of each s term, we can find whether it is stable or not, right? So the condition is the value of a0, a1 and a2 should be non-zero, right? for first order system and second order system, we can easily find out. That is the conclusion, right? Now, we'll move to the next one, n equal to 3. So the polynomial becomes a0 s cube plus a1 s square plus a2 s plus a3. Right. Okay. So I will give two third order polynomials. You find the roots and tell me. First one is s cube plus 2 s square plus 3s plus 1. And another third order polynomial is s cube plus 2 s square plus s plus 3. And one thing you observe that all the coefficients of s term are non-zero, right? This is 1, 2, 3, 1, and the second polynomial also having the coefficients greater than 0. It is a non-zero value. So according to this Hurtiz polynomial concept, what we are one thing first will come into our mind is both systems are stable, right? Correct? Now you find the roots of this and take the calculator and tell me what is the roots of this. What are the rules for of d1 of s? No, d for d1 of s. 1.3j, yeah, fine. Minus 1.30. Okay, clear. And what about the second? Fine. What about the second one? Minus 2.17. Yeah. Yeah. So what you observe from this? See, in our polynomial, all the coefficients are positive only. What we did, see, compared to d1 of s, what is the specialty in d2s? I just swapped the coefficients of this time, right? Here it was 3 and 1. Now I put 1 here and put 3 last. But you observed that if I locate the roots of both, this is real, this is for the second system. You can see that one is at minus 0.43 and other one is at is minus 0.78. So one is somewhere here, is plus 1.3j and The other one is at minus 1.3j. Right. So what you observe from this, all the three roots are in which plane? LHP, right? So that means your system is stable. Right. Now we will move to this polynomial. You can see that one pole is at minus 2.17. Right. So what about the other? These are the RSP, right? 0.08 becomes somewhere here. So one you can locate here is plus 1.17J, and the other one you can locate here. This minus 1.17. Oh, sorry. Just gone. Sorry, once again I have to draw it. It just not saved automatically, just closed. Do you have class next hour? Okay. So while seeing this, you can understand that here all the roots are in LHP. So system is stable. And what about this? Here you can see that one pole is at LHP, right? And the other two poles are at RSP. So what do you understand from this analysis? So while seeing the one for the polynomial would be is said to be Hurtiz, means all the roots have negative real parts, right? For first order system and second order system, it is fine, right? While seeing the polarity of each coefficients, you can tell that our pole is at either left side or right side of the S-plane. But if you are going for third order or more than that, that is not the necessary condition to judge the stability of the system. I mean, it is not the sufficient condition to judge the stability of the system, right? The necessary condition is all the coefficients, all the polarity of the coefficients should be greater than 0 and means non-zero and have the same sign, right? But we need a sufficient condition to judge the stability of the system, that you can differentiate from this, right? These two. So while seeing the constant values, we cannot tell whether the poles are staying in the left side or right side. So we need a sufficient condition to judge the stability criteria. So that's why we need a Hurtiz stability criteria. Clear? Anyway, I get all those points here, you'll know. necessary condition is all the coefficients must be non-zero and of the same side. Okay. This is the necessary condition. But for order is equal to greater than or equal to 3, this necessary condition alone is insufficient to judge the stability rate condition, so that we need a sufficient condition. Right. So in order to find that sufficient condition, what we have to do, we need to construct a root array. So this is the final topic we are going to study. So hope everyone understood why we need to construct the root array, or why we need another method to find the stability, another method called root stability criterion to judge the stability of the system. Clear? So in order to find that sufficient condition, we are constructing the root array. So tomorrow we will see how to construct the root array using the polynomial, characteristic polynomial, and how to judge the characteristics of the system.